career sections. And the first speaker is Tseng from Yonsei University. Okay, talking about neutron decay anomaly.
Good afternoon, everyone. So in this talk, I will talk about some neutron dark decay models, which was originally proposed to explain the neutron lifetime anomaly. And I will discuss some signature from the underground water Cherenkov detector, and we will see which kind of signature is able to search or explore this kind of dark decay models. And yesterday, we already gave a very nice introduction about this topic, and therefore I will more focus on some detail in our analysis. And this work also collaborate with Daniel Mafakia. So the neutron lifetime anomalies come from two different experimental methods to measure the neutron lifetime. One of them is called the bottle experiment, and the other is called the bin experiment. So for the bottle experiment, they prepare the neutron called neutron inside the container, and they really count the total number of the neutron as a function of time, so they can extract the lifetime of the neutron. And for the bin experiment, they prepare the neutron bin, and they detect the proton final state from the neutron decay to proton or anything else possible. So the value from these two measurements actually are related to the branching ratio of the neutron to proton decay branching ratio. However, from the standard model, this branching ratio is almost 100%. It's from the inverse beta decay. So in the standard model, they predict the value from these two experiments should be equal to each other. However, over the 20 years, this figure is showing the average result from the bin experiment and the bottle experiment. Turns out there is, for sigma, tension between these two different kind of experiments. And therefore, to explain this anomaly, there requires some 1% of the neutron decay into non-proton final state. And more specifically, the Forno and the Greenstein, they proposed a microscopic model to describe this, to allow the neutron decay into a chi particle to be a good parameter candidate associated with the photon in the final state. And also a more complex, the model 2, which allow the neutron completely decay invisibly. So in model 1, they introduced a new capital phi, which is a QCD triplet. So from one side, this capital phi coupled to the down and the up quark. On the other side, coupled to the down and the chi particle. So this process actually violates the baryon number. And for the model 2, there's two more additional particles being introduced called the chi theta and the phi. So in this case, more parameters space will appear in the model 2, and therefore it's difficult to constrain the model 2 parameter space. And because this capital phi carry the QCD charge, so it should be heavier than TeV scale, otherwise the LHC will easily produce the capital phi particle. And because it is heavy and therefore in the GeV scale, this operator can be shrunk into a point contact interaction and described by some effective interaction. So it will look like a mixing between the neutron and the high particle, and the mixing angle should be parameterized like this way. And the photon can emit from this process through the neutron magnetic interaction. And on the other hand, the neutron also coupled to the pion through this interaction, but the pion is too heavy to be produced from the neutron decay. But this interaction also will be relevant to our later discussion about the signal, because the neutron had the pion had a quite large coupling with the neutron, so they can enhance the production cross-section. And since they introduced a particle around the GeV scale, in order to consistent with all the experiment observation, turns out very narrow parameter region is allowed for the mass of the tiny particle. So the upper limit is come from the proton plus electron mass, which stabilize, doesn't allow the chi decay into proton and electron. Turns out the chi become a stable particle, so it becomes a good diameter candidate. And the lower bound of the mass is come from require the proton should be stable, otherwise the proton will decay into chi and the electron. However, more stringent constraint will come from the stability of the beryllium 9. So turns out this beryllium 9 gives a more stringent constraint than the proton decay constraint. And for model 2, as you can see, at least that there are 3 mass being involved in this model. So actually the parameter space can be slightly extended. So more obviously, we can look at this colored region, which satisfy the parameter space described by these 3 inequality. And this vertical black line is correspond to the parameter region for the model 2. So the model 1 can slightly extend the parameter region to lower chi-square mass, or even a little bit heavier than the model 1 case. So from this process, we are thinking about what kind of signal on the other experimental detector we can solve to explore this kind of model. So if we can move the chi particle from final state to the initial state, it becomes a chi bar particle annihilate with the neutron and produce a photon signal. And in order to balance the kinematic additional particle, we choose using the pion to attach to the neutron. So turn out the signal will be like something diameter annihilate with the neutron and produce 3 photon signal. So this signal should be very clean and easy to distinguish from the background. And similar signal can be seen from the model 2, but they will have additional missing energy in the final state. Then which kind of experiment is the ideal environment to detect this kind of process? I already showed the answer. So the diameter can come from the halo around our galaxy, and we only need to prepare the huge detector with the many neutron as a detector. Then we just detect the GeV photon signal. So it's similar like diameter direct detection. However, the diameter, instead of scattering with the neutron, but the diameter just annihilate with the neutron and produce much higher energy photon signal. So we think super Cavalcante or future hyper Cavalcante and doing experiment, they have a huge detector volume, and their PMT can also receive the GeV photon signal. So we think this is the ideal experiment environment to search this kind of signal. So then we able to calculate how many events we can see from this experiment. So first, for the model 1, we choose 2 benchmark points. As we can see, the mixing angle between the neutron and the chi actually is very small. They only need 10 to the minus 10 or 10 to the minus 11 to explain the neutron lifetime anomaly. And an even smaller mixing angle is required by the model 2, is about 10 to the 12 or 10 to the 11. And the P3, because the chi mass is very close to the upper limit, therefore the decay width being suppressed by the phase space. So you need to compensate by slightly larger mixing angle to produce the same amount of neutron star decay. So that's the reason the mixing angle for point 3 is slightly larger than point 1 and point 2. And however, the event rate from our calculation is very pessimistic. For the super K, they maybe barely see the event rate. And for the model 2, it's almost impossible to see any event from this kind of signal. However, this monophoton and the neutral pion signal is not the dominant annihilation process. If we recall the neutron anti-neutron annihilation or anti-neutron photon annihilation, actually the multi-pion is the dominant annihilation cross-section. And this branching ratio is simulated from the super K's papers. However, the multi-pion cross-section is non-perturbative. It's not easy to direct calculate by perturbative method because the pion and neutron coupling is close to the perturbative limit. So instead, we try to use in the data-driven method from this data point, which is correspond to different incoming anti-neutron momentum. Then we just extrapolate it down to the 0 momentum limit. Then we obtain the cross-section is about 44 millibar. Then for the diameter annihilate with the neutron, we just multiply by the mixing angle square to this experimental value. So this is just total cross-section. For more detailing, we also need to work out the distribution, kinematic distribution of our signal. And we think our signal will be very similar to the anti-neutron neutron oscillation signal from the super K. So, and the super K already performed such kind of analysis as they focus on this kinematic region, that this is the total momentum of the final state, and this is the invariant mass of the final state. And from their observation, they saw 24 signal events, and it's perfectly consistent with the background. Therefore, they put a very stringent upper limit for the allowed event from additional from physics beyond STEM model is around 22 or 23. And for hyper K, we just rescale this observation up to the detector sensitivity. So we obtain the upper limit should be 75. And for Dune is around 27. And for Cut2 and Cut3 is not so relevant because they was using for the proton decay search. So we performed some Onde-Carlo simulation for our signal distribution project at this total momentum and the invariance plan. So the dash box is the cut Super K was using to search the anti-neutron neutron oscillation signal. So as we can see, our signal distribution had a lot of overlap with their kinematic region. And so this is for model 1 annihilated into 3 neutral pion. And this is for model 2 with 3 neutral pion associated with some missing energy. So the distribution was slightly skewed to the lower invariant mass region, but still not overlap with the signal region. So from here we can roughly understand how many percentage of our event can pass the kinematic cut. So especially for multi-pion case, most of them, about more than 50% of the event can pass the kinematic cut. So we are using this, we can obtain how many event rate we can see from the Super K, Hyper K, and the Dune experiment. So for the model 1, almost 1 million event we can detect from the current Super K sensitivity. Therefore, the model 1 can be already been ruled out by the Super K current observation. And however, for model 2, since the P3 point had a slightly larger missing angle, so the cross section will be larger, therefore the event rate is more significant and already being ruled out by the current Super K observation. And for point 1, it's just barely seen by the Super K experiment, just right on the top of 3 sigma upper limit. And however, the point 2, because they have heavier mediator mass, the chi theta, therefore the chi theta will suppress the cross section, so make the event rates very small for the point 2. So even in the future Hyper K detector still cannot reach this. Point 2 still cannot be reached by future Hyper K experiment. So I'll summarize here. We studied the possible signature from neutron dark decay model, which was originally proposed to solve the neutron lifetime anomaly. And we think the Super K Hyper K Dune will be the ideal environment to search for the signal. And we consider the photon plus neutron pion. So this signal will be very clean to see. However, the cross section is too small. So for alternative, we looking for the multi-pion signal. They have more huge cross section. Therefore, the model 1 can be ruled out by the current anti-neutron neutron oscillation search by Super K. And model 2, because it has more parameter space, it's difficult to be fully excluded. But most of the parameter space can be covered by future Hyper K and the Dune experiment. Yeah, thank you.
Questions? Just a quick one. Now it seems that the neutron star is free to decay now. It's open up its channel. So what's the constraint?
For neutron star, yeah, if the neutron can decay to dark matter, then neutron star will disappear. However, if you can add some repulsive interaction between the dark matter, either dark matter self-interaction or interaction between neutron or dark matter, they will stabilize the neutron star. So neutron star still can survive.
How many year one or hyper K then can do out the CM?
Hyper K, we assume 20 years long.
Okay, 20 years.
Yeah,
20 years.
They will have 20 times more data than super K.
Go back to the previous slide. So for the massless pi in the model 2,
Yeah.
so should we need to worry about any other constraints?
For massless. Yeah, probably. This is stable, but you can give them slightly mass and they will decay before the end or so. Yeah, avoid them.
Let's do it.
In principle, K can carry baryon number and then preserve the baryon number.
It is conserved. It is conserved.
Or
Then-
model 2 is.
Then if the
Both are
dark,
conserved. Both are conserved.
if the dark matter is also asymmetric, is mostly carry with K with positive baryon number, then you cannot annihilate neutron by the baryon number conservation.
Yeah.
The early residue, they annihilate. There are some residue.
Yeah, but your estimate is, do you assume that all the dark matters are made of the K? And the
Yeah. Actually, there are two choices. Only the Chi bar will annihilate with
Right,
Chi.
yeah.
So we may assuming all the dark matter is composed by Chi bar. But or if it's 50%, 50%, then or even signal will be reduced by 50%.
But if it's very small, then it doesn't constrain.
Yeah, yeah.
Okay, so let's take 4页。